Without further ado, I guess we can move on, and I can introduce the first speaker, who is Vikas Krishnamurthy from University of Vienna, and he will present his joint work with Miles Wheeler and Darren Crowdy and Adrian Constantin, and he will talk about hybrid equilibria of Stuart Vortices and point vortices. So Vikas, the virtual floor is yours, please. I guess everybody should be able to see Vikas' slides. Vikas, please.
Thank you, Bartek. So thank you for the introduction, and I'd like to first thank the organizers of this mini symposium for providing me the opportunity to talk here, and also particularly for the late changes to our topic and so on. And so yeah, so I'll be talking today about some new exact solutions of the Euler equation that we uncovered recently, and this is joint work with Miles Wheeler, Darren Crowdy, and Adrian Constantin. So let me begin by introducing the governing equations of motion. So we are looking at the two-dimensional flow of an incompressible inviscid fluid. We have the 2D Euler equation. And then from the incompressibility condition, we get the existence of a stream function psi. Then we introduce the vorticity, which for this 2D flow has only a single component, and the vorticity and the stream function are related by equation 4. And by eliminating the pressure terms from the Euler equation, we get the vorticity equation in terms of the stream function psi. Okay, so we then look at the two main types of vortices that we are interested in, point vortices and Stuart vortices. So first, just to remind everyone of point vortices, they are solutions of the unsteady vorticity equation, where the vorticity is a bunch of Dirac delta functions. Gamma j are the circulation of the vortices, and they move about under the influence of each other according to equation 7. Z here is the complex plane, over bars denote complex conjugates. What we are interested in are particular configurations of point vortices called point vortex equilibria. So so relative equilibria of these point vortices are where they're stationary with respect to each other, so they can be translating rigidly or rotating rigidly. But in particular, we are interested in completely stationary equilibria, where all the vortices are stationary, so all their velocities are 0 and they do not move. Some sort of background motivation on why these point vortex equilibria are interesting. As we all know, coherent vortex structures are observed in a large variety of fluid flows. Just a few select examples where such equilibrium states are observed in the lab and in numerical simulations is shown here. The first one is figure 1 is basically in a magnetized electron plasma, whose equations are which basically can be shown to obey the same equations as point vortices. And then you also have here in figures 3 and 4. Well, figure 3 is basically an experimental setup of water in a rotating tank. Figure 4 is the emergence of vortices in some simulations of turbulence. And so basically there's a lot of, there's a wide interest in looking at equilibrium configurations of these point vortices. Okay, so now we move on to look at Stuart vortices. So they are, unlike the point vortices, solutions of the steady vorticity equation. And it's really easy to see that the steady vorticity equation is solved by taking the vorticity to be some function of the stream function. And in particular, if you take the vorticity to be exponentially related to the stream function, you get the Liouville differential equation, which is equation 9 here. A and B are some constants. And explicit solutions of this Liouville differential equation are available, and that's shown in equation 10. So now here, as we see, the vorticity is basic. I mean, it's not a irrotational flow; it's a rotational flow, and the vorticity is non-zero everywhere because it's exponential. And nevertheless, and so there is therefore no complex potential for this flow. Nevertheless, the solution for the stream function is given in terms of a single analytic function of z, which is h of z. H prime is its derivative. And so in terms of this function, you have the solution for the stream function. So I'd just like to point out one detail. If you look at the formula for the stream function, you see in the denominator of the log, there is a 1 plus mod h squared. And this turns out to be important later on for us in the sense that if this 1 plus wasn't there, then it would simply be a irrotational flow. So this is sort of a seemingly simple modification to get a rotational flow, and it's an exact solution of the Liouville equation. So this equation has been studied in the context of vortex dynamics, and the resulting solutions are called Stuart Vortices after Stuart's study in the context of mixing layers, where he found this first figure at the top with the cat's eye pattern streamline patterns. It's also been studied by Crowdy on a sphere and Sakaja on a torus, but we are not discussing these geometries today. Okay, so I want to just state what our main results are. So firstly, what is the problem we are interested in? So we seek solutions to the modified Liouville equation. So modified meaning that you take the Liouville equation, which is the first part in equation 11, and you add a bunch of point vortices to the vorticity. So you basically have the delta functions. And away from the point vortices, you simply have the Liouville equation, and therefore the solution of the Liouville equation continues to hold. But because the point vortices are in general going to be unsteady, you need an extra condition that the velocity calculated at the location of each of the point vortices, and this velocity is calculated as in 12, sort of in a similar manner to how you would calculate in an irrotational flow. You take the whole velocity and you subtract the infinite self-induced part. And so all of these point vortex velocities defined as in 12 have to be 0. So in short, if we add a bunch of point vortices into a sea of Stuart vorticity, will it work, and what are the conditions under which it will work? Okay, so we have got two main results. The first one seemingly has got nothing to do with the problem that I just formulated, and it's actually a result that is purely concerned with point vortex equilibria. But this is a new result. And what we have here is that supposing you define a function h prime as in 13, which basically, so zj's are where the point vortices are, gamma j's are the circulation, capital A is just some constant, non-zero, doesn't matter what it is. So you form this function from a point vortex equilibrium. So h prime is some known point vortex stationary equilibrium. Then you define this new function h hat prime through this mathematical transformation of h. Now notice that we have defined h prime, and in the transformation we have both h prime and its primitive h. So you define this new function h hat prime, where again these a hat, alpha, they're all some constants, it doesn't matter. And so what you can show then is that if the point vortex circulations are either positive integers, half integers, or -1, then this new h hat prime will first of all be of the same form as h prime, that is, it will be a rational function. And secondly, that all the vortices will be in equilibrium, and this equilibrium is distinct from the one that you started out with. So this is the first main result that we have purely concerning point vortices, but it is very closely related to the modified Liouville problem that we were just looking at. And so the relation is that you take the solution of the Liouville equation, which is 15, and you simply plug in the H prime, which is any point vortex equilibrium that is given to you, and you will have a solution of the modified Liouville equation, as long as the circulations obey 14. And so basically, you end up with a bunch of point vortices embedded in a sea of Stuart Vorticity. So I'm not going to actually discuss the how to prove this and so on. Instead, I'll just go straight to examples to sort of explain what's happening and also to see what the properties of these solutions are. Okay, so let's look at examples. So firstly, let's go back to Stuart's original solution, and what he was trying to do, in fact, was, if you notice, I mean, I've just set some constants A and B to be some value, is unimportant, but so the psi that you see is the solution of the Liouville equation, right? And then what you, the function H prime has a 0 somewhere, then you have a logarithmic singularity at that point. Now, Stuart wanted smooth solutions, and he wasn't interested in having singularities in the flow. So what he did was he took the choice H is some A times tangent function, and then with this you get everywhere smooth solutions. So I'll come back to the singularities of psi in the next example, but let's now look at what happens as you vary this parameter A. So you can substitute this H prime and you do some rearrangement and you get the psi as seen in the box. And what happens is that A can, without loss of generality, you can take that A goes from 0 to infinity and is a real number. And what happens is that you find that as A goes to 0, there's one of the terms in the log drops out. As A goes to infinity, another term in the log drops out. So basically, as A goes to 0 or infinity, you get a periodic row of point vortices the stream function for a periodic row of point vortices. But for any finite A, you get a combination, and this is rotational solutions, and that's the cat psi pattern that's again periodic, of course, but that is everywhere smooth, and there are no singularities anywhere. So this is what Stuart found. And what we are interested in, on the other hand, is to deliberately add singularities and to find the conditions under which they will be point vortices. So let's consider a simple function like A times Z, okay? So this is the stream function, and once again, you can do some rearrangements, and this time what you actually find is that in the limits as A tends to 0 or infinity, whereas in the previous, let me just go back a second. In the previous case, as A goes to 0 or infinity, they're just space shifted versions of the same thing. It's either cos or sine, so it's just the same thing. But here what you find is, in fact, you end up with either a log mod Z, which is just a single point vortex, or or basically Z squared by 2 plus C over mod Z, the second part of the log, which corresponds to 3 point vortices. C here is just an integration constant that you get after integrating H prime. That's all. And so as A tends to infinity, you now get a different stream function corresponding to a point vortex equilibrium with 3 point vortices in it. And for all intermediate A, you get rotational solutions with where in place of, whereas before you had a everywhere smooth solution in with Stuart's choice, in this case, because H prime has a singularity, and maybe it's just clear to, yeah, so if you just go back a slide, you can see here that there's a singularity at Z equal to 0. So you will end up with a point vortex at Z equal to 0. You can show this. And then you also have the solution depending on the parameter C, which can be complex. And if you vary C, you see, in this case, for example, the topology of the solution changes. So this is like a simple example. So let me now come to a more general description of what's happening. Is that, so the first result sort of is a discrete transformation, in the sense that it takes you from a given point vortex equilibrium into another new distinct point vortex equilibrium. Okay, but we also have a second result which connects these sort of first one, which is purely about point vortices, to the Lewin equation, which is a rotational flow, and says that between these two limiting point vortex and flows in otherwise irrotational flow, you have a rotational solution for every finite value of A. And in this sense, this is a sort of a continuous branch of solutions of the Euler equation. So it's a continuous via modified Lewin. So that's the second result. And in some cases, it turns out you can do this forever, in the sense that you take the second point vortex limit that you just got with the 3-point vortices, and you say that, okay, so you can iterate it again, and you can get, or you can transform it again, and you can get a different point vortex equilibrium with higher numbers of point vortices, and you can also have a hybrid solution, i.e. a solution with, a solution of the modified Lewin equation in between these limits. And you can go on forever. At each stage, you get a new equilibrium with higher numbers of point vortices. So I must explain that in these plots, all the blue markers are positive point vortices, and the black circles are negative point vortices. Sometimes we also use blue pluses for positive point vortices. And there are also these integration constants, and in the case of iterating solutions, you have a new integration constant at every step, and you can change these integration constants to changing them does various things. One of the things it does is it introduces asymmetry. It can also, for example, change the number of point vortices, but I don't discuss that today. So just to be clear, these the solution, the patterns that you see now are all for C chosen to be such that they're all symmetric, and then you can change them so that the resulting plots become asymmetric. The resulting equilibria and also the corresponding hybrid equilibria become asymmetric. Okay, so here's another example with which is a single stage transformation, in the sense that you cannot iterate this one. As I said, there's some conditions under which you can iterate, and some conditions under which you can only do it once. But you can always do it once. If you are given any point vortex equilibrium, you can always transform it once into a new equilibrium, as long as the conditions on the vortex trends hold. So in this case, you have some 3 vortex equilibrium that is transformed into 3, 6, I think that's, okay, that's 11 vortices. And so that's the discrete transformation. And then you can also have a hybrid equilibrium with these 2 point vortex equilibria as the limits. And what you can see shown in the hybrid equilibria panels here is sort of what happens as you vary the parameters A and C. When A is small and going to 0, you can see that in the hybrid equilibrium, there are just the 2 point vortices and then some very concentrated vorticity in place of the point vortex at the origin. And then as you increase A from 0, you get you see the appearance of these new centers. Basically, as A goes to infinity, the vorticity starts to concentrate at these centers, and at infinity, you end up with the transform point vortex equilibrium. The second row in the hybrid equilibria panel is just showing the same thing, but with different choices for C. So you can see the asymmetry and so on. We can we can find many different families of iterated equilibria. These are ones in terms of Adler-Moser polynomials. So Adler-Moser polynomials, for those who may not know, are basically, they arose in a very different context when people were looking at rational solutions of the KdV equation. And it turns out that those rational solutions are given in terms of the Adler-Moser polynomials. In the context of vortex equilibria, it turns out that if you have point vortices of strength plus minus 1, and you ask when they are in stationary equilibria, it turns out that they are in equilibrium if they are at the roots of successive Adler-Moser polynomials. And so you can produce this hierarchy with the transformation that we saw earlier. And so what's shown are the first few such point vortex equilibria and the corresponding hybrid equilibrium for some intermediate value of A. And one of the things you can notice if you look at the last panel for the hybrid equilibrium here at the bottom right is that the vorticity, well, the limit A tends to 0 or infinity is not uniform in space. So you can see the vorticity concentrating already at some points and not so much at others. And this is the same thing, but again, there is a new integration constant at every step. So at the nth stage, you have a solution that depends on n complex parameters, n arbitrary complex parameters, and given explicitly, and changing them changes, well, obviously changes the centers and so on. And it can also do other things like it can increase or decrease, well, it cannot increase, but it can decrease the number of vortices and change their strengths. But we won't discuss that today. Okay, so so to summarize, we have two main results. One is a transformation that takes a given stationary point vortex equilibrium into a new distinct stationary point vortex equilibrium, and a hybrid equilibrium with solution of the modified Liouville equation exists between these two stationary point vortex equilibria, and it continuously interpolates and extrapolates between these two point vortex equilibria. And then there are iterated versions of both types of equilibria under certain conditions. So for the future, there are actually many different things that it appears can be done with this. So it can be generalized to periodic flows or flows on a sphere or torus, etc. And also there's the question of more general rotational limits of rotational solutions of the Euler equation. And finally, there's lots of connections to mathematical physics. We just mentioned one with the Adler-Moser polynomials, but there are many other connections which have yet to be explored. And these are some of the publications related to this. I didn't. So the last two are with. Well, are related to some applications of these exact solutions to geophysical fluid flows, and I haven't had time to discuss those today, but the first two are basically well, they contain the results that that we saw, and there are a few more sort of in preparation. So thank you for your attention.
Well, thank you very much, Vikas. I guess we can virtually clap, we can virtually applaud. So I guess I would like to invite session participants to ask questions using the Q&A panel. So I guess I should be able to see those questions, and we'll read them out to Vikas. Vikas, can you see the question, or should I read it out for you?
I can see the question.
Yeah, maybe it will be simpler if you can just answer it. Yeah.
Okay. So, so the first question is from Mark Stendler. It says, have you looked at quantifying the relative strength of the point vortices and the Stuart vortices as A varies under some definition of what constitutes a concentrated Stuart vortex? Yeah, so I'm not sure if I fully understand the question, but yeah, I mean if you so what's happening is, if I can just go back, yeah, so if we look at, for example, this, well, maybe even this, yeah, so the vorticity is concentrating at these centers, and the question of what happens to, so for example, we can look at what happens to the total circulation in the rotational solution, and it's actually possible to provide a formula for the total circulation in terms of the total circulation of the point vortex limiting equilibria. And it turns out that the total circulation for the rotational solution is actually independent of A. So it doesn't really change as you change A. I'm not sure if that exactly is what the question was asking. But in terms of, I mean, so the relative strengths of the point vortices already present in the rotational flow to the well, I mean, we do know what the strengths of the point vortices in the limiting equilibria are. So I guess that, combined with the fact that the total circulation. Okay, so so I guess there's a follow-up is, what's the relative significance of the point vortices being singularities? Yeah, so yeah, so I guess, I mean, it's not. So it's not actually fully clear which point vortices that you start out with will remain as point vortices in the rotational flow. So as far as in this figure, for example, you can see that so these pluses are positive point vortices, and so what happens is that basically, if you compare, you can clearly see that it's only the positive point vortices that remain, and the negative point vortices are basically what are sort of smeared out into the to become the Stuart vorticity. But this is strictly true if you have negative vortices of strength -1. In some cases, you can have other strengths, but and they kind of do various things, and it's not yet clear to us what exactly happens.
All right. Any other questions? If not, then I actually have a quick question. I was wondering if you could clarify the significance of the black circles and blue diamonds. What is what?
Oh, sorry. Yeah.
For example, in the
so the black circles are negative point vortices, and the blue diamonds are positive point vortices.
Okay, and the size reflects the.
Yeah. So the size reflects the strength. Yes. Sorry, I should have mentioned that at the beginning.
Okay. Sure.
Yeah. So and in the hybrid plots, the pluses are the positive point vortices. Again, their size reflects their strength.
Right. Thank you.
No problem.
Any other questions, comments? Well, if that's not the case, then I guess we can thank Vikas. Thanks a lot. So we can virtually